Have you ever left a stainless steel knife sitting in a sink full of water overnight, pulled it out the next morning, and found it exactly as you left it? Bright, clean, completely unaffected. Then you pick up a regular steel nail that rolled behind the kitchen bin 3 weeks ago, and it is orange. Completely orange. The same base material, more or less. Completely different outcome. And you have accepted this difference your entire life without once asking what actually separates them. It is not a coating. It is not a treatment applied to the surface that wears off over time. It is not that stainless steel is somehow sealed against moisture in the way a painted surface is sealed. The knife in your drawer has no protective layer that could be scratched away to reveal vulnerable metal beneath. You can score it, grind it, cut it, and the protection comes back. Instantly, invisibly, and without any intervention from you. Steel is one of the most widely used structural materials in human history. It builds bridges, reinforces concrete, forms the skeleton of every tall building on Earth. It also rusts with a consistency and speed that engineers have been trying to manage for as long as it has existed. Rust costs the global economy hundreds of billions of dollars every year in damaged infrastructure, failed components, and maintenance. The question of how to protect iron and steel from oxidation was one of the defining engineering problems of the Industrial Revolution, and it remained largely unsolved for nearly a century after steel production became industrialized. The answer, when it arrived, came from a direction nobody had been looking. But here's the surprising truth. Stainless steel does not resist rust by preventing the metal from reacting with oxygen. It resists rust by reacting with oxygen faster than iron can, using a sacrificial element that forms a barrier so thin it is invisible to the naked eye, so stable it lasts for decades, and so chemically active that it repairs itself the moment it is damaged. Today, we're unpacking what that element is, why the self-repairing barrier works when every other method of protecting steel eventually fails, and how a chance discovery in a Sheffield laboratory in the early 20th century changed every kitchen, every hospital, and every aircraft ever built. To understand why ordinary steel rusts so readily, you have to understand what rust actually is and why iron is so prone to it. Iron atoms have an inherent tendency to bond with oxygen. Left exposed to air and moisture, iron loses electrons to oxygen molecules in a chemical reaction that produces iron oxide, the reddish-brown compound we call rust. The reaction is self-perpetuating and structurally destructive. Unlike the oxide layers that form on some other metals, iron oxide is porous and flaky. It does not adhere tightly to the surface beneath it. It crumbles, exposing fresh iron, which oxidizes in turn, which crumbles, in a cycle that continues until the metal is consumed entirely. A steel nail left outdoors does not develop a protective crust. It develops an advancing front. Every approach to protecting steel before stainless steel was invented worked by placing something between the iron and the oxygen. Paint, galvanizing with zinc, tin plating, electroplating with nickel or chromium. Each method was effective until the barrier was breached, and each barrier was eventually breached by wear, impact, scratching, or simple time. The protection was always external to the steel itself, always finite, and always dependent on maintenance to remain effective. The flaw was structural. You were protecting a reactive material by covering it with something else, and coverage is never perfect. Think of it like trying to keep rain off a wooden floor by laying a rug over it. The rug works while it is intact and positioned correctly. The moment it shifts, gets a hole, or is lifted at an edge, the wood is exposed to exactly the moisture it was supposed to be protected from. The wood itself has not changed. The moment the covering fails, the underlying vulnerability is exactly as it was before. What the engineers working on steel protection in the 19th and early 20th centuries needed was not a better rug. They needed wood that didn't absorb water. That is effectively what chromium does when added to steel in sufficient quantities. The discovery is generally credited to Harry Brearley, a metallurgist working in Sheffield in 1913, who was searching for an alloy that could resist erosion in rifle barrels rather than oxidation in kitchens. Testing a range of steel compositions with varying chromium content, he noticed that some of his experimental samples failed to stain when exposed to acid and moisture in the way ordinary steel would. He set those samples aside. A journalist later coined the term stainless steel, and the material was in commercial production within a decade. The mechanism that Brearley had stumbled onto is called passivation, and it works through a logic that is almost the opposite of conventional rust prevention. Chromium, when present in steel at a concentration of roughly 10.5% or more by weight, reacts with oxygen in the surrounding air spontaneously and extremely rapidly. Before iron in the alloy has a significant opportunity to oxidize, the chromium has already done so, forming a microscopically thin, tightly adhering layer of chromium oxide across the entire exposed surface. That layer is chemically stable, electrically non-conductive, and physically dense enough to exclude both oxygen and moisture from the iron beneath it. Unlike iron oxide, which is porous and crumbles away, chromium oxide bonds firmly to the surface and holds. The behavior that makes this genuinely remarkable is what happens when the layer is damaged. Scratch stainless steel deep enough to remove the oxide layer entirely and expose bare metal to air. The chromium in the freshly exposed alloy reacts with oxygen immediately and reforms the passive layer within seconds to minutes, depending on the conditions. The protection is not a coating applied once. It is a continuous chemical process that the material performs on itself, indefinitely, as long as chromium is present in the alloy and oxygen is present in the environment. So, if chromium oxide is this effective, why does stainless steel eventually stain or corrode in certain conditions? The answer, as is often the case in history, comes down to what the passive layer is and is not resistant to. Chromium oxide provides robust protection against oxidation from air and water. It is significantly less resistant to chloride ions, which disrupt the electrical structure of the oxide layer and can create localized sites where iron beneath is exposed. Salt water, chlorinated swimming pool water, and prolonged contact with salt residue on a surface can all compromise the passive layer faster than it can reform. This is why marine-grade stainless steel, used in boat fittings and coastal architecture, uses a different alloy composition with added molybdenum, which reinforces the passive layer against chloride attack. The protection scales with the threat. The self-healing chemistry can be tuned by adjusting what else is in the alloy alongside the chromium. There is also a category of stainless steel corrosion that looks like rust but is not. Ordinary carbon steel particles from a steel scouring pad or a cast iron pan left resting on a stainless surface can embed in the surface and rust on their own, leaving stains that appear to be the stainless steel itself corroding. Remove the embedded particles, and the stainless steel beneath is untouched. The surface has not failed. It has been contaminated by something that does not share its chemistry. So, the next time you pull a stainless steel knife from a sink full of water and set it down without thinking, you'll know what you're holding. not a metal with a protective coating. A metal performing a continuous chemical reaction with the air around it, forming and reforming an invisible barrier faster than oxygen can reach the iron beneath. Harry Brearley was looking for something that wouldn't wear away under friction. He found something that couldn't be permanently damaged at all. The most durable surfaces are not the ones that resist attack. They are the ones that recover from it.